Hello, so now we're going to talk about curve sketching, okay? We're going to use the ideas from the earlier sections to help us sketch a nice curve of the graph of a particular function, okay? Now, if you're looking at my notes, there's some guidelines for curve sketching. Also, if you look in the book, they go through the same guidelines, maybe with more words that I put. I kind of just put the main ideas behind them. But the first thing is find the domain. Okay, you want to know where you're drawing this graph on, so you need to find the domain of the function. Secondly, find the x and y intercepts. Those give you some starting points to put on the graph. Next, check for symmetry, meaning if the graph is symmetric about the y-axis or the origin, you know how to draw it because the left half of the graph is going to match the right half of the graph depending on the symmetry. Next, you find the intervals of increasing and decreasing, because then you know where should you be drawing increasing intervals, decreasing intervals. Next, you find any local mins or maxes, because then you know exactly where to draw them, instead of just randomly putting them where you think they should go. And next, find the intervals of concavity and find the points of inflection. So those really help when drawing those minimums and maximums, those valleys and those hills. So let's go ahead and use this information. I know I have on my paper y. I'm going to make it f of x. F of x equals x to the fifth minus 5x. Okay? Now the first thing we're going to find is the domain. Now this one's really easy because it is a polynomial. So therefore the domain is from negative infinity to positive infinity. Okay? For other functions it may be a little more different. You may have to set the denominator equal to 0 and solve. Maybe it's a log function. Who knows? But this one's a polynomial. There's our domain. Next, let's go ahead and find the x and y intercepts. So for the x-intercepts, we plug in 0 for f of x and solve for x. So x to the fifth minus 5x equals 0. Well, now we just got to factor this. I could take out an x. I get x to the fourth minus 5 equals 0. This right here is a not perfect square trinomial, difference of squares problem. It's x to the fourth minus 5. This is an even power. It'd be just like if it was x squared minus 5. You could factor it into an x minus square root 5 times x plus square root 5. That's if it was a square, but since it was a fourth power, that's going to be squared and that's going to be squared, and we still have it equal to 0. Now this right here is a sum of squares. This one doesn't factor any further, so we can't do anything with it. We're going to leave it alone. Okay, this does not give us any x-intercepts. This one, however, can factor even further. It is another difference of squares. So x times x minus, now we got to take the square root of the square root. That is going to be the fourth root of 5 times x plus the fourth root of 5 times x squared plus square root of 5 equals 0. So we can see right there that's going to give us 0. Right here that's going to give us positive fourth root of 5. It's a really bad 5. And right here is going to give us negative fourth root of 5. Okay, so here are all the x-intercepts. So to find the x-intercepts, you set your function equal to 0 and factor until you get these values. Okay, so we have x-intercepts at the point 0, 0 and plus or minus the fourth root of 5, 0. Okay, so now to find the y-intercepts, to find the y-intercepts, all you do is plug in 0 into this expression and solve for y. So y is equal to 0 to the 5th power minus 5 times 0. Well, that's 0. Okay? So we have a y-intercept at 0, 0, which we already knew about because our x-intercept also was at 0. So these 2 points are incidentally the same. That's not going to be true for every single problem. Okay? Now what we're going to do is we're going to check for symmetry. And if you recall, oh, I erased my function. F of x equal x to the 5th minus 5x. If you recall, an even function is when you plug in negative x and you get back out the same exact function. An odd function, you plug in negative x and you get back negative of the original function. Now, this will help us draw the graph if the function is even or odd. Because if the function is even, we know it's symmetric about the y-axis. So, however we draw the graph on the left is going to look exactly how it is drawn on the right. If it's an odd function, it does have symmetry, but the symmetry is about the origin. Okay? However we draw it in the first quadrant is going to be reversed how we draw it in the third quadrant. Same how we draw it in the second quadrant, it's going to be reversed how we draw it in the fourth quadrant. It's symmetric about the origin. Now, not every function has to have symmetry. There are functions that don't have any symmetry at all. So we might not be able to use symmetry to help us draw it. So let's go ahead and check for symmetry in this function. I'm just going to plug in negative x to the 5th minus 5 times negative x. This is negative x to the 5th without the parentheses plus 5x. Now if we look at this, it looks almost identical. Okay? Let's factor out a negative. I put a squared here. That should be a 5th. If you notice, this is the exact original function that we had. In other words, it's equal to negative f of x. So that means this is an odd function. We have the condition f of negative x equals negative f of x. So f is odd. All right. Now let's see. Find asymptotes. Okay? This function does not have any asymptotes. To find vertical asymptotes, you would set the denominator equal to 0 and solve. Okay? This doesn't have any denominators. So we cannot do that. Secondly, to find horizontal asymptotes, what we can do is something we learned back in section, or in chapter 2, limits at infinity. So we could take the limit as x goes to infinity, or it actually doesn't matter, plus or minus infinity of our function, and if it equals L, it equals a finite number, then L is a horizontal asymptote. However, since this is a polynomial, all polynomial functions have a basic shape to them. If it's an even function, they look like this or they look like that, generally. They may have some little humps in here in the middle. An odd function always looks like this or it looks like this, okay? So as you can see, as I go off to positive, and this is an odd function, if I go up to positive infinity, or if I go x goes to positive infinity, I go up to infinity. If I go x to negative infinity, it goes down to negative infinity. So this does not have any vertical or horizontal asymptotes. In the next example, we'll have some asymptotes, but not in this one. So let's record that. No asymptotes. Find the intervals of increasing and decreasing. Okay, so if you recalled how we did that, you have to take the derivative f prime of x is equal to 5x to the fourth minus 5. Just a simple power rule. And the first thing we needed to do was find the critical numbers. So, critical numbers, you just take the derivative, set it equal to 0, and solve. So I'm going to take the derivative, 5x to the fourth minus 5, set that equal to 0. And now let's go ahead and factor out the 5. We get x to the fourth minus 1 equals 0. We look at the 5. This factors into an x squared minus 1, x squared plus 1 equals 0. Another difference of squares, it factors one more time. X plus 1, x minus 1, x squared plus 1 equals 0. So we could see that we get a critical number from this one and we get a critical number from this one. Our critical numbers are going to be plus and minus 1. Okay? I'll put c is equal to plus or minus 1. Okay? We still needed our derivative, f prime of x. I don't know why I erased it. Now, what we're going to do is apply the increasing, decreasing test that we learned in section 4.1 to go ahead and find the intervals of increasing and decreasing, okay? So, to do that, we made a number line, if you recall. We put our critical numbers on the number line, and then what we did, we picked test values from each interval to check whether that interval is increasing or decreasing. So we've got the red interval right there. We've got the green interval right there. And we also have the blue interval over here. So if I'm picking test values, I'm going to pick 2 right there. Let's see, I want to pick negative 2 over here. And then in the middle, because I could pick 0, I'm going to pick that. So now what you do is you plug your test values into the derivative and see whether they're greater than 0 or less than 0, depending whether or not you're finding intervals of increase or decrease. Let's say we're finding the increasing intervals. So that's f prime of x is greater than 0. So let's find f prime of negative 2. And let's see if this is greater than 0. All I'm doing is picking my test values, plugging them into the derivative. Okay? 5 times negative 2 to the fourth minus 5, is that greater than 0? Negative 2 to the fourth power is positive 16. 16 times 5 is 80. So we get 80 here, minus 5 is greater than 0. We get 75 is greater than 0. Is 75 greater than 0? It is greater than 0. So this interval right here worked. Okay? So we know we're increasing from negative infinity to negative 1. So let's go ahead and do another test value. F prime of 0 is equal to, is this greater than 0? That's what I meant to put. Is this greater than 0? Well, 0 is really easy to plug into there. F prime of 0 is equal to, if I plug 0 into there, we get negative 5. Is negative 5 greater than 0? Negative 5 is not greater than 0, so this test value did not work. Now, if we try this one more time with our last test value, f prime of 2, just plug in 2 into there. We get 5 times 2 to the fourth power minus 5. Is this greater than 0? Well, 2 to the 4th power, just like negative 2 to the 4th power in parentheses is also 16. 16 times 5 is 80. 80 minus 5 is 75. Is 75 greater than 0? It is, okay? So now we have our intervals of increase, and then this would be our interval of decrease, okay? So let's go ahead and record this. I'm starting to run out of room. Increasing interval is from negative infinity to negative 2, union 1, or sorry, not to negative 2. I picked the test value to negative 1. And then from 1 to positive infinity, the decreasing intervals is between here, from negative 1 to 1. Okay, so again, getting crowded, running out of room to put stuff up here. It's okay though. Let's see, local mins and local maximums. So, to find local mins and local maximums, we have our critical numbers right here, okay? We have to determine whether positive 1 is a local min or max, or if negative 1 is a local minimum or a maximum, okay? Now, since we already found the increasing and decreasing intervals, it would, in my opinion, you should just do the first derivative test, because in order to do the first derivative test, you would have had to find these increasing intervals anyways, okay? So, at c is equal to, let's do negative 1. If you look at what we found here, let's draw our number line again. Right here's negative 1, right here's positive 1, okay? Over here it was increasing, over here is decreasing, over here it was increasing. If you go back and look at the first derivative test, it said that at a critical number, if on the left side it's increasing of the critical number, and then on the right side it's decreasing on the other side of the critical number, that is the definition, or sorry, that's not the definition, that is the result of a local maximum. So think about it. Increasing, decreasing. Right here, right there was negative 1. It has a maximum. I'm increasing all the way through here, and then I'm decreasing through there. All the tangents are positive until I get over here. The tangents are negative. So going from increasing to decreasing is a maximum. Now if we do it on this side, decreasing to increasing, let's go ahead and look. Decreasing to increasing. Everywhere here my graph is negative. Sorry, my derivative is negative, so I'm decreasing. Over here it's positive. Right here would be like 1. So it has to be a local minimum. Okay? So now that we have the critical numbers, we could say there's a local min at 1, local max at 2. Almost done. Find the intervals of concavity and points of inflection. So if I want concavity, that's second derivative. 20x to the third. All I did was take the derivative of f prime. Now, inflection points. You take the second derivative, set it equal to 0, and solve. That's all you do. Second derivative equal to 0, solve. So, 20x cubed equals 0. Well, that just means we're at 0, okay? The only solution to this is 0. So, inflection point x equals 0. Now, we want to find the intervals of concavity. That is very much like the first derivative test. However, you're using concavity test, instead of using the critical numbers to put on your number line, you're putting the inflection points on your number line. So now you just pick test values. Let's see, -1, +1. And you see whether you are positive or negative on that interval. So let's say we are, if f double prime of x is greater than 0, this is concave up. So let's take our test value and plug it in here. F double prime of -1 is equal to 20x, sorry, not x, we're plugging in -1, -1 to the third, which is -20. Is this greater than 0? We're looking for concave up intervals, so it need to be greater than 0. Is this greater than 0 at -1? It is not, okay? So that means on this interval, we are concave down. Now, if we were to do it on the other side, if I just plug in 1 here, the negative goes away, the negative goes away. Is 20 greater than 0? It is. So over here, we're concave. Ooh. I wrote down here. This should have been up. Over here, we're concave down. All right, so now I have all of my information that I need to draw this, sketch this curve. So let's see, concave up is from -infinity to 0. Concave down is from 0 to +infinity. Okay. Let's go ahead and sketch this curve now. Local max at 2? I don't think so. Local max at -1. I don't know why I put a 2 there. It should have been -1. It's one of the critical numbers. We determined that was a min at 1, max at -1. So that's what I'm going to put on here. I'm going to put all my x values that I need on here. So I've got a, over here is at -1. And then over here is at +1. Now, if we wanted to actually find the minimum or maximum value, we know we have a minimum value at 1 and the maximum value at -1. All you would have to do is take these numbers and plug them into the function to get the actual y values, okay? So, if I were to plug in 1 into here, we get 1 to the 5th power, which is 1, minus 5 times 1, which is 5. So 1 minus 5 is -4. So at 1, we're at 1, 2, 3, -4. And if I were to put -1 into here, it's going to be -1 plus 5, which is +4. 1, 2, 3, 4. As you can see, you're already starting to see some odd symmetry. Up here in the second quadrant, it's exactly drawn, but opposite. If I were to reflect it over the origin, it's exactly drawn the same way, okay? It's an odd function. All right, let's see. We've got x-intercepts at the 4th root of 5, okay? Now, that's really hard to put on a graph. The 4th root of 5 is an irrational number. You could go ahead and plug it in the calculator and get a good number for it. I'm just going to estimate about where it's at. Let's say it's like right there. And then that means the other one is right there. So this one is the 4th root of 5. And then this one right here is -4th root of 5. Alright, so let's see. What else do we have to put on here? We've got an x-intercept and a y-intercept right there. Okay, now inflection point 0. I think we have all the points that we should have up here. Okay, now let's go ahead and draw the graph. Now, we're concave down. I think I switched these. I did switch them. This is concave down, concave up. My apologies. Okay. 4 through to 5. Actually, yeah, it's over here. 4 through to 5. I have it wrong in my head. I thought it was less than that. It's somewhere over here. -4 through to 5. There we go. Now, we're concave down from -infinity to 0. So, from -infinity to 0, we're concave down. Okay? That fits the idea that it's a maximum right here. So, it's got to go like this, and it goes down like that. Okay? So, you see, on this entire interval from -infinity all the way to 0, we're concave down. Not only that, look at our increasing interval. It goes from -infinity to 1. So it goes from -infinity, x equals -infinity, all the way up to -1. I'm increasing all the way through here. Now I'm decreasing through here, like that. As you can see, I'm decreasing from -1 to 1. And then it passes through my other x-intercept, and I'm increasing again from 1 to infinity, 1 to infinity. Not only that, you could see it's concave up from 0 to infinity. Okay? So this would be the graph of the function. Okay? And as you can see, we drew it really accurately. Okay? We've got where the local mins and maxes are. We got the exact point of inflection. We got the exact x and y intercepts. Okay? So we could draw a really detailed graph using these new methods that we have. In pre-calc, you learn how to sketch graphs as well. However, when you sketch those graphs, they were all based on the end behaviors and the zeros of the function. Previously, you were not able to find local mins and maxes or inflection points because you needed the derivative. So this just adds on to the ability to sketch graphs continued on from pre-calc. In pre-calc, you would have found increasing, decreasing, or actually you wouldn't have found those. My apologies. You would have found these. See, you would have found the asymptotes, but you would have found them in different ways. And then you would plot the zeros and kind of, I got a 0 there, I got a 0 there, got a 0 there. The end behaviors like that, that's how I would draw it. But now calculus allows us to find these points and find these points right there to give us a better drawing of the graph. Now, my recommendation to you guys is when you get done drawing one of these graphs, go ahead and plug this into your calculator and look at the shape of the graph. If you have the basic shape and your points are labeled nicely, you could check them, you probably have the right answer, okay?